hopefully. All right. So so how do we do this? This is one-to-one in inverse functions, this section 5.2. I think this would be pretty, not too bad. Is that a one-to-one function? Well, the name gives it away. Is it one item in the domain with one item in the range? Is that one-to-one? One-to-one? Well, yeah, just look at it. It's not if it has something like, if you have one thing going to two things or something like that, then it's pretty obvious. That would be a not. That says not if you have something like this. So this one's a yes. That one's one-to-one, easy enough. Functions in different settings, right? So now they're going to say, okay, so here you got like order pairs. Remember how like when they go 4, 9, that's x, y, 3, 6, that's x, y, negative 8, 3, that's x, y, and 1, negative 8, that's x, y. You can just look at it like that. If it bugs you, you can rewrite it and put all the x's here and the y's here. Right, that's what domain and range is, x and y, right? So that'd be 4 goes to 9. That's what 4, 9 means, right? 3 goes to 6. You don't have to do this, but if it helps you, okay. Negative 8 goes to 3, 1 goes to negative 8. So is it a one-to-one? Yeah. One-to-one, Again, you don't have to write the arrow diagram thing, but if you can just see that by looking at the pairs, that's fine. So, on a graph, you're one-to-one if you pass both the vertical and horizontal line tests. I know they're only mentioning the horizontal because it's already a function. Remember, to be a function, you got to pass the vertical. So if we have something like, so let me come down here. If we have something like this, that's not a function, because it fails the vertical line test, right? Remember, if a vertical line hits more than 1 point, it's not a function. Well, what about like y equals x squared? Well, that fails. That one's a function, but it's not one-to-one. It's a function, but not one-to-one, right? It passes the vertical line test, right? Every vertical line only hits 1 point, but it fails the horizontal line test. Y equals x squared fails the horizontal line test. So it's a function, but it's not a one-to-one function. Does that make sense? There's different categories. There's just being a function. If you pass the vertical line test, then higher level of standard. Are you the best kind of function, a one-to-one function? Well, no, y equals x squared is not a one-to-one function. Why not? Can you tell me some x, y where they would double up? Yeah, negative 1-to-1 and 1-to-1, huh? Right? Both those go to the same y value, don't they? Both those x's go to the same y, right? If we did an arrow diagram, we'd have negative 1 and 1, both going to 1. Huh? It's not 1-to-1. It's a function, but it's not 1-to-1. So it fails the horizontal line. Is that 1-to-1? No. Because you got to pass both tests to be 1-to-1. Try that again. Oop, the answer is yes, because I did the wrong. They just had that graph. So that one, yeah, failed. It passes the horizontal line test. Horizontal line hits only 1 point, right? So there's only one x for one y, according to that function. I did it wrong. Let me do it right. I was just thinking about the vertical thing. I just got my mind focused on the vertical thing. No, that's going to fail the horizontal line test all over the place. Yeah, no, it's a function, but it's not 1-to-1 because horizontal line hits 2 points, right? All right, we want to get to inverse functions. So let's get to inverse functions. So which of these two, this one or this one, is the inverse function of that? It's this one, right? It just simply just turned it around, right? That's all inverse. Invert the x's and y's. That's all an inverse function is. They're just making sure you got the big idea, the basic idea of what is an inverse function. That's what we're about in this section. It's when you take a function and you just swap the inputs and the outputs, the x's and the y's. They just trade spots, domain and range. Just switch them. So there it is. That's an inverse function. So which one of those is inverse? Well, again, it's when you switch x and y, switch x and y, switch x and y, switch x and y, switch x and y. That's an inverse function. So which one of those has all the x and y's switched? Yeah, it looks like C, doesn't it? Yeah. Good? Easy enough. That's all inverse means, to invert x and y, right? Not equations, but function notation. Okay, algebraic notation. All right, so what do they want me to do? In part A, they want me to find f of g of x. That's what you did in last night's homework, right? So they want me to take g, right, and put it into f. So we can do that. We did that last night. Take all of g and put it in the input slot of f, right? So 3 times all of g plus 9. And what is g? G is 1/3 x minus 9. We good to there? So I put all of g into f. F was 3 times whatever plus 9, right? Work that out. What happens? 3 and 1/3 just cancel right away, huh? So we just get x minus, and you can drop all those parentheses, which is just x. Remember we talked about what that means, right? What does that mean when you take one something and put it in both machines and it comes back the way it started? Yeah, so if I took a piece of bread, I put it in my toaster, come out toast, put the toast in my detoaster, come back to bread. Right? That proves that the detoaster's undoing what the toaster did, right? Opposite machines. That's what it means. That's what we just did here. Because x went into g, came out of g, went into f, and came out the same way it started, right? X. So when you run something through two machines and it comes back the way it started, that means one of those machines is the opposite of the other. It's undoing whatever the first machine did, right? That proves they're inverse functions. That's what they're looking for in this one. They're trying to say, hey, what does that mean? So they're going to have you do it both ways. They're going to say, put g into f, now put f into g. It'll come out x. In both cases, it'll come out equaling x. In other words, it'll come back the way it started. So if you run through both machines, either direction, it'll come back the way it started because those are inverse machines. And then they say, determine whether they're inverses. Well, in part C, you'll say, yes. Yes, they are inverses, because it's coming back the way it started. That's one of the ways to test if two functions are actually inverses. You just run something through both of them, right? You just put one machine inside the other and see if it comes back x. If so, yeah, it must be undoing. One machine must be undoing the other. They might not come out x. They might sneak one in that's not x. But yeah, I agree with you, Robert. The first one comes out x, the second one's going to too. So f of g. So they want me to do f of g of x. So they want me to take all of g and put it in both x slots, right? You always stick the stuff that the x's are the holes in the toaster. They're insert slots, right? So we'll go, okay, what a mess. 5, and then, well, here, let me just do the thingers. It's going to be 3x minus 4 over 5 minus x, and this will be 3x minus 4 over 5 minus x, like that. And then that's going to be plus 4, plus 4. All right. So I just stick all of g into f. What an ugly mess. All right. Can you clean all that up? And we're hoping it's just x. I don't know if it's just x. So what should you do to clean this up?
Times 5 minus x to the 3 and 4 and the rest of the equation.
Yeah. Right. Remember when we have fractions over fractions? Something you want to be comfortable with when you get to calculus. Fractions over fractions. You want to multiply all four. Well, first off, I think this 5 kind of bugs us. Where's this 5 going to go? Yeah, it's 5. It's 5. Any whole number is always over 1, huh? So just let it go to the top. I think that might be nice. Just to get him taken care of. 15x minus 20. Let's just get him out of the way because he's kind of weird looking. A little better to there, like that. Right? Any whole number interacting with a fraction is just over 1, let it go, right? So we good to there? Yeah, now it looks a little more regular. You know what to do. Whenever we have fractions over fractions, you always put your eyes on the denominators. Those are the only denominators, right? And multiply all the terms, bless you, all the terms by that denominator, right? So I'll go 5 minus x, 5 minus x, 5 minus x, 5 minus x. And these two cancel. That's why we're doing it, because we want to get rid of those denominators so we can just make it a normal fraction instead of a complex fraction. The other ones will multiply, right? The 4 will go boom, boom. The 3 will go boom, boom. The other ones canceled away. So what do we have? 15x minus 20 plus 20 minus 4x over 3x minus 4 plus 15 minus 3. See how I got all that? Everybody good with what happened? So these canceled. Here's the 15 minus 20. 15x minus 20. Good. And then I multiplied the 4 to both those. 20 minus 4x. On the bottom, the 5 minus x is canceled. That was the whole reason we did it. Bring down the 3x minus 4. And here the 3 multiplies both those, 15 minus 3x. Good so far. And then these cancel. 15x minus 4x is what, 11x over. These cancel. Over 11. Hey, it is just x. Wow. Look at that. So we're going to do the whole thing on part B then? We're going to say x. And we're going to say yes. So again, it's just x, yes. It could have been no. I mean, it could have not come out x. They're giving us all ones that do. Anyway, is that good there? That makes sense? So those really are opposite machines, aren't they? They must be. Because whatever you put into both of them comes back the way it started. X went into G, then went into F, and came out as just X again. That's what that's telling us. Came out as just X again. Now we're graphing inverse functions. All right, so they're basically giving us this graph, the blue. The blue there is the graph of F. And they want me to draw the graph of F inverse. So let's be clear for a second. F has the following points. 3, 5. I'm just looking at the graph. I'm just looking right there at that graph. 3, 5. 1, 2. Negative 1, 1. And what's that one? Negative 5, negative 5. Okay. So what does that mean then about what points will be on F inverse? What does an inverse function do? Swap, 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 swap. It's just going to switch the coordinates, huh? So 3, 5 will lead to 5, 3. 1, 2 will lead to 2, 1. Negative 1, 1 will lead to 1, negative 1. And negative 5 will stay the same. Because it swaps them and they're already the same. So put those dots. Go over to the graph then and put those dots. So over 5 up 3. Where's that? Over 5 up. Oh, is it? Yeah, I'm going to do it here first, then I'll look down the options. There's 5, 3. Over 2 up 1 is about right there, I think. Supposed to connect those two, huh? Everybody good there? It's 5, 3, 2, 1. And then 1, negative 1, over 1, down 1 right there. Boom. Over 1, down 1. And then negative 5, which is that same dot right there. There it is. Everybody see how I did that? Yeah, and it is A, huh? That's right. Make sense? Now, why do you think they put that diagonal line in the middle? The y equals x diagonal line. What do you notice about the visual image? Yeah, it's a reflection, isn't it? The inverse function is, the red inverse function is a reflection of the original function. Reflection across the diagonal line, isn't it? And that's the truth for every inverse function. That's why they gave us that to help us out. Every inverse function is a reflection of the original function across the y equals x diagonal line. This is y equals x. Right? Why? Why is that the case? Well, because what do you do when you make an inverse function? You switch x and y, right? That's the diagonal line is all the points where y is the same as x, exactly equals x, y equals x, right? So therefore, when you switch x and y, it's going to go across that line, exactly across that line, because the x and y values have been switched. So we can expect that. So, all right, good. All right, so now they're going to give us a function in algebraic notation, and they want us to find the inverse. So what are the steps for finding an inverse given an algebraic format? Number one, yeah, you switch. We've seen that you got to switch x and y, don't you? Right? When you're given points, you switch x and y. Given a graph, you switch x and y. Given tables, you switch x and y. So it makes sense, given algebraic notation, you switch x and y. And step 2, solve for y. Because y is always the function, so after switching, y will be the new function, the inverse function. That's really it. 2 steps. Switch x and y, solve for y. So take the equation, f of x equals x cubed minus 2. What is f of x really? That's y, as we said, right? Function letters, f of x, g of x, h of x, those are always y values by common agreement. That was just, everybody agreed. On a graph, we're going to make function values be the y-axis. It was just common agreement. Okay, so step 1, switch them. Switch x, y. And what that means is that literally means just trade roles. Y becomes x becomes y. Just like that. That makes sense there? Just trade roles. Step 2, right? Because that's what they do, right? That's what it means to be an inverse function. Inputs have become outputs. X's have become y's. Solve for y. Why do we solve for y? Because y is going to be the new function. Y always represents functions. Now that we've made the switch, we've created the inverse function, we just got to solve for it now. So how do you solve that little equation for y? Add the 2 to both sides. X plus 2 is y cubed. Then what do? Cube root it, right. So we'll go, okay, cube root. So the cube root of x plus 2 is y. You know, cube roots cancel the cube. There it is. The inverse function is the cube root of x plus 2. That's the opposite machine. It makes sense, doesn't it? Right? If your original one is third power minus 2, then the opposite is the third root of the thing with 2 added. It's opposite. Exactly the opposite, isn't it? I think it's all. Oh no, they want the domain and range and all that kind of stuff. Okay, we'll do that. Let's do that. Is that too quick? Everybody get that down? Everybody good there? So they want me to do domain and range. Okay, so let's do that. They want what? Domain of f. Okay, what's the domain? What's f again? F is the original. X cubed minus 2. Okay, so what's the domain of him? We've learned how to do, we've done a lot of domain, haven't we? You guys are domain pros, right? So what's the domain of x cubed minus 2? Correct. All real numbers. There's no problems there, right? Remember how it works? I know we cover so many things so fast. But remember, domain, when you're looking at an algebraic format, means look for trouble spots. No knives in the toaster. Domain means what's allowed to be plugged in. And you only look for 2 trouble spots given algebraic notation. Square roots and denominators, right? The inside of a square root must be only positive, greater than or equal to 0. And a denominator cannot equal 0. Well, we don't have either one of those. We don't have any roots or denominators. So all reals, or negative infinity, positive infinity. I don't care how you say it on a test. Any of those are fine with me. Right? Okay, so that's the domain of f. See how that's what they're asking in part B. Now look how they're what they're saying. C. Oh no, domain and range. Okay, yeah. They also want the range of f. I'll come back to that. Let me just move ahead and I'll show you a real tricky way. Now on part C, let's find the domain of f inverse. That means inverse function. Okay, and now what's that going to be? Well, here's the inverse function. The inverse function is right here. Third root of x plus 2. What is it, Robert? All reals? Excellent. Everybody realize what Robert's realizing? Third roots, who cares? Remember, the problem is only even roots. Remember, you can take the cube root of a -8. For example, it's -2. Remember, no problem having negatives in an odd root. Only even rooters have a negative inside problem, right? You guys with me? Cube root of -8, you can do that. It's -2. -2 times -2 times -2. 3 times would be -8. You can do odd roots of negative. Odd rooters have no problems in life. It's only the even rooters that have the hang-ups, right? Only even rooters said, no negatives for me. Because you can't have something an even amount of times come out negative. But odd is fine. So yeah, so Robert's right. It's all reals again. It's all reals. Okay, now, I bet you can figure this out without me hardly saying anything. So we've got the domain of f, right? And they also want the range of f. And down here we have the domain of f inverse, and they also want the range of f inverse. Now remember, what's an inverse function compared to the original? You switch x and y. Switch inputs and outputs. Switch domain and range. So the domain of f is going to be what? The same as what? The range of f inverse. And 1 from now on these so we can get through, because some of them are messy. I want to make sure I show you those. All right, let's try that one. So I'm just going to do the step A. You can go as far as you want, but in a second I'm going to start with y equals 5 over x. Find the inverse. So what do? Switch x and y, solve for y, right? Go through those two steps. Find the inverse. Switch x and y. Like so. Step 2. Solve for y. How do you solve that for y? What do you do? A lot of things you can do. I would just put this over 1 and diagonal. Cross multiply. Whenever I just have one fraction on one side and a whole number, just put it over 1 and then cross multiply, right? X times y is 1 times 5, meaning x times y is 5. How do you finish solving for y now? Divide by the x. Y is 5x. In other words, it came out the same as the original. This is a function whose inverse is the same as his original. It's weird. The rest of the parts are normal. What's the domain of that thing? See, I always want to do the whole thing. What's the domain? X can't be 0. Anything else is fine, right? You can't have 0 on the bottom. And that's going to be the domain for f inverse, and that's therefore also the range for both. The domain and the range for both f and inverse, since they're the same function, is going to be x could be anything but 0. And then you just graph them. All right, let's try that one. So, two over 4 plus x. Find the inverse function. Switch x and y. Solve for. I pretty much do the same thing. Cross multiply and be very similar to the last one, except it won't be itself. It'll be different. The inverse function won't be exactly the same as the original this time. So, step 1. Switch or invert. So x goes out here, y goes over there. Good so far. So you switch x and y, or f and x, however you want to say it. Switch them. Step 2, solve for the y. How do you solve for y? Put this over 1, diagonal. Everybody good with that so far? And then distribute. 4x plus xy. 1 times 2 is 2. Like so. Good. How do you solve? Y's over here saying, I want to be alone. So subtract 4x. xy is 2 minus 4x. Last step. Divide by x. Can I cancel these x's here like this? Why not? This minus says, hey, we are a package deal. Right? Remember, plus and minuses glue things together. Which means if you want to do anything on that top, you go like that and buy the whole top. You cancel the whole top or none of it. It's all or nothing. When there's plus or minuses, it glues things together. All or nothing. We can't take all, so we take nothing. So it just stays like that, huh? That's the inverse function. All right, let's graph those. Oh, let's find the what's the we can do all the domain and range stuff. So what's the domain of f? denominator not equal to 0, so x cannot be negative 4, huh? Anything else is fine, right? That'd be the domain of f. And what's the domain of f inverse? Denominator cannot be 0, yeah. And therefore, what's the range of the original function f? X cannot be 0 because it's the range of f inverse becomes the domain of f. Right? Remember the switcheroo thing? We good? Am I going too fast? Am I losing you? Right? So the domain of f inverse, x, the denominator can't be 0, and that is also the range of f. And then what is the range of f inverse? Yeah, x cannot be negative 4, which was the domain of f. Domain of f becomes the range of f inverse. So we got all that domain and range stuff. That's questions. Oh, did they? Oh, they didn't ask me that this time. Or did they? Yeah, I guess they did. Yeah. Anyway. Oh, they don't want a graph. Okay. Well, then I'm done. That's everything. Questions on that one? All right. So we've got the original function y equals 6x plus 6 over 9x minus 5. All right. Can you find the inverse? Let's do it. Step 1, switch them. So this becomes x. And both of those y's, x's become y's. Good to there? So y becomes x and both x's become y. X's become y's and y's becomes x's. Inputs and outputs switch. That's an inverse function. Now solve that for y. That's going to be harder. If you did that one other time. See if you remember what you remember about that. Solve that for y. So I give you the x, put it over 1, cross multiply thing, right? But it's going to get a little more tricky after that. Over 1, diagonal, diagonal. Right, this is all normal. Nothing new here so far. Distribute 9xy, 5x, xy plus 6, right? This is all step 2. Solve for y. Normal to there, right? Good so far? Now, what are we trying to solve for? Y. We want to get y alone. And notice that y is in 2 locations, not just 1 location. That's the harder thing, right? I think we've done that one other time, haven't we? What do you do when you're trying to solve for a letter that's in like 2 places? Yeah, get those 2 together on the same side, factor out the y, and divide. That's the game plan. Whenever you're solving for something that's in 2 places, it's going to come up a lot and a lot in calculus. You got to get just to where this is not just a small speed bump for you. You go right over it without a problem. So that's going to take practice. So that means you got to get this guy over here and this guy over there. Switch those. When things jump to the other side of the equal sign, they just change the sign in front of them, right? Just a shortcut for adding 5x to both sides and subtracting 6y from both sides, right? And I'll get 9xy plus 6y. No, minus, huh? Minus 6y equals positive 5x plus 6. Make sense so far? I just got both the y terms on the same side. Now factor out the y and divide. That's how you isolate it when it's in 2 places. Factor out the y, 9x minus 6. Is that good? And divide. So I'll bring it up here. So, whoops. So divide. Boom, y's alone. There's the inverse function. So, let me write a note on that. when y in two places, well, when y is in two places, get both y's on the same side, factor out y, and divide. So when the y is in two places, get both y's on the same side, factor out y, and divide. You can read all that scribbling in the corner. Is that okay? It'll come up a lot. Make sure you're comfortable with doing that. That kind of thing will happen in a lot of scenarios. Questions? We good? Found the inverse. And then the rest, I don't know what else they ask. What else do they ask? I can't read that now. They want the inverse. Okay, find the inverse. We did that. Find the domain of f. Find the range of both. Domain of f. Well, that's easy. That's just denominator not equal to 0. So nothing amazing there. All right, I'll move on. Okay, so looking at the graph, what is f of negative 5? Just from the graph. Yeah, because remember, this is an x and it's asking you for the y. Well, here they are right there. There's the x and y that go together on the graph. All right, so that's part A. Part B says what's f of 4? Can you tell from the graph? What's f of 4? Yeah, it is 5, because again, that's the x, that's the y. It's the point right there. X, y, 4, 5. They're basically saying on the graph of f, what x goes with what y? X4 goes with y5 according to the graph. Now we're going to change gears in part C. They're saying f inverse of 0. Inverse. Yeah, so this is the y and this is the x then, huh? For the inverse function, you've switched x and y. So they're saying what y value of 0, right there, goes with some x value. The x value is negative 4. That's easy, right? You got it? They're just switching them. Just making sure you're getting that idea of switching them up on the graph. Let's do that one other one, see if that one's hard. Let's try it. So 25. All right. So y equals x squared minus 1 over 4 squared. It wants me to find the inverse. So you know the deal. Step 1, switch them. So this is x. These guys are both y. Looks normal enough right now. And then what do we do now? Now you want to solve for y. That's step 2. Let's put this over 1, diagonal, diagonal. 4xy squared, 1 times y squared minus 1, which does nothing. Everybody good to there so far? Right, so I just put it over 1, cross multiply. Now I'm trying to solve for y. So what should I do? Yeah, get the two y squared terms on the same side. Same, when you have two locations again, right? Get them on the same side. So jump this over. Let me bring it up to here. So I got 4x y squared minus y squared, right? When it jumps over, it becomes a negative y squared. I basically subtracted y squared from both sides. Then what? Factor it out. Divide. So y squared is 1 over 4x minus 1. And now what do we have to do? Going to have to root it, huh? But when we put a roof on the house, got to go up and down the ladder, don't we? For a square root, for even roots. So y is plus or minus square root of 1 over 4x minus 1. Now, which one is it? Do they want me to type in like plus and minus?
No, they just want the square root.
How do you know?
I already did that.
Okay, good. That's a good reason. How about a logical reason?
Because you can't have negative.
Why not?
You can't have a negative.
Who said it? What's that?
Robert said it.
Robert said it, so it's done. No. Who says? Look right there. They said. They said X. No, hold on. Wait a minute. Wait. Let's be careful. They said X is bigger than 0. And this is why. I'm saying y can be positive or negative, but they said x can only be positive. X got to be greater than 0, right? X only positive. X only positive. So, but I'm trying to say something about y? Come on, give me the answer. I'll let you go.
Because they're inverse.
They're inverse. So the x here is the y for the inverse. So the y is only positive. That's why. All right, we're out of time. This is due tomorrow on Math Excel, which it already says. Have a good day.